Hello again, we are still talking about window functions in SQL. And we are nearing the end of this particular chapter. It's a long chapter, the longest chapter yet. I think the longest chapter is yet to come. It's about recursion, but window functions deserve their time and space. We are almost done though. So we have talked about window functions that aggregate rows in a frame. We have talked about window functions that allow for positional access inside a frame, either relative to the current row or absolute inside the frame. And there's a third group of window functions, which is the topic of this video and then the last video in this chapter 5. And that would be functions that allow us to number and to rank rows. There's countless scenarios where you would want to number or rank the rows inside a table based on given ordering criteria. And once you have the number, the position number or the rank of a particular row in hand, you can use that later on in a query to compare rows, to order rows, to group rows. There's countless opportunities to use the numbering and ranking window functions. There's not too many of them. You see them listed here in this small display. We will draw a line between them at this point because, well, you see that there are of different flavor. But we will first talk about row number, dense rank, and rank. So numbering and ranking rows. And these are more advanced functions, actually. And if you look closer at them, they can actually be expressed by the first three. So there's some syntactic sugaring going on here. Okay. So what's common for these is that the frame is irrelevant. We are looking at all the rows inside a partition, or even all the rows if there is no partitioning involved. But what should be involved, what is really crucial for these functions to make any sense, is an ordering, a well-defined ordering as specified by the order by clause here in the window functions, using ordering criteria as you are used to knowing by now. So ranking without order by is really questionable. I think the system will let you pass and will let you do it, but what you get is a completely random or non-deterministic result. Okay, so all of these normally go with a well-defined ordering on the rows, and based on that ordering we will number the rows. So let's see how that could work. Okay, so this is a display that shows the first three of the ranking and numbering functions in SQL in action. The base, again, is some input table that we have ordered according to some criteria. In this case, it's just a single column A. So that would be our ordering criterion. And as you can see, we have ordered the table in an ascending fashion, so that this row with the smallest A value is on the top, and that this row with the largest A value is at the bottom. That's no coincidence. Okay. So if this is the well-defined order established by the order by criterion, then this is what row numbering would give us. It's just the numbering of the rows, a unique numbering of the rows in the A order. Okay, it's really a unique numbering. We could use the row numbers, the row number function, window function, as shown here in the first column. We could use the values emitted by this function as key values. Okay. As you can see, there is some rows here, the rows row 3, row 4, row 5, these guys, or these two rows, row 7 and row 8, they agree on their A value, so there is no well-defined ordering regarding the ordering criterion A. What you will get as a row numbering is random, in a sense that any of these three rows could have been the row with row number 3, 4, and 5. The one ordering has been chosen by the implementation of PostgreSQL, and that's the ordering in which the rows will be numbered. The numbers will be unique, so 9 rows lead to row numbers from 1 to 9. Okay. It's different for the two sister functions, the ranking functions. Whenever rows agree on their ordering criteria, they are ranked equally. Okay, so because these three values agree on their A value, they get the same dense rank and the same rank assigned. As you can see, the rank increases as we walk down the table, but rows with equal that have equal sorting criteria are being ranked equally. All right. Once we are past this row of equally ranked rows, the ranking just goes on, as you can see here. Okay. There's a slight difference between the dense rank and the rank function, and you see this when you look at these ranking gaps here. So where dense rank switches ranks from 3 to 4, rank switches from 3 to 6. And this is just the semantics of the ranking function. It's much more like the assignment of ranks if you think about sports or Olympics maybe. So if these three guys share the third place, the third rank, then there is no fourth and fifth rank, and we continue the ranking with the sixth rank here, as you can see. The same down here, both rows, row 7 and row 8, share rank 7, so there is no row at rank 8, and we continue with 9 here, though there is a gap. So what you will see is this general comparison of ranks that are assigned to the rows inside a table. Okay, for all of these we will find countless applications. While row numbering might be or might look useful at the first glance, it's all of these have their uses, and we will see all of them put to good use during the course of the lecture and the entire course actually. Okay, so that's row numbering and row ranking. Okay, so let's briefly switch over to the terminal here. There you go. And I brought this ranking and numbering example with me. You see that I'm repeating the setup from the slide that we have just seen, but I've thrown an ordering into the mix here. Okay, so all of this is again exercised over the playground table W, which I remind you of here. Okay, ordering criterion A, partitioning criterion B. This is the playground table. So we will now partition it by the B column, so into the black and white circles. Inside the partition, we will order by the A values, and then the row numbering and the ranking is performed. So let's see what we get here. All right, so indeed, we have separated the rows into the black and white circled rows. These are the two partitions. Inside each partition, everything is ordered in a ascending order. All right, this looks good to me. Okay, and then we are ready to start the numbering. So there is 5 rows in the black circle partition, and indeed the row numbers, they go from 1 up to 5. There are 4 rows in the white partition, and the row numbers go up from 1 to 5 here. Okay, so indeed row numbering and ranking is performed in a partition-wise fashion. Okay, what about the ranking? So there is indeed 2 rows that rank equally according to our ordering criterion A, and they receive the same ranks indeed. But dense rank continues with rank 3, rank continues with rank 4. And you will see a very similar pattern down here in the other partition. All right, so much for just the basics of numbering and ranking. So what can you do with this stuff? Quite a lot, as I told you. We could, for example, return to our dinosaurs example. If you recall, we had that example of a dinosaurs table. In particular, all of these dinosaurs had been assigned a number of legs, either 2, 4, or an unknown number of legs. All right, and I think at one point we were wondering about the three tallest dinosaurs in the 2-legged and in the 4-legged group. Okay. Back then we found a solution, but row numbering and ranking, they suggest alternative, quite compact and elegant solutions, I would say. And that solution is displayed here in the query below. Okay, so that's a nested query. A subquery is involved. I will come to this in a minute, but let's read the query from the inside out. All right, so let's first look at the subquery here. This is the subquery. It goes from here to there. Okay, so we would of course look at the dinosaurs table. We would disregard all the dinosaurs for which we don't know anything about the number of legs. So we are only looking at the 2 and the 4-legged dinosaur groups here. And inside each group, we are on the lookout for the 3 tallest dinosaurs. So inside each leg group. So it should be no surprise that you see this partitioning clause here. Okay, we are iterating over all the dinosaurs, but we are separating them, we are grouping them, partitioning them into the 2-legged and the 4-legged dinosaurs. This is being performed by the partition by. Then we are on the lookout for the tallest dinosaurs. So the height of the dinosaurs will be the ordering criterion here. And indeed, this is what you see here in the order by clause. Since we are interested in the tallest dinosaurs first, we will order the dinosaurs by descending height. So the first dinosaur in this ordering will be the tallest dinosaurs. Okay. According to this ordering, the height of the dinosaurs, we will simply rank them. We will rank the dinosaurs and just assign these integers 1, 2, 3, and so on. Dinosaurs of the same height will receive the same rank. This is a consequence of my choice to work with rank here in this box. All right. We can look at the consequences of choosing row number instead in just a second. Okay, so what comes out of this is a 4-column table, legs, species, height table, and additional column n is generated, which reflects the ranking of the dinosaur regarding its height in its leg group. Okay, since we are interested in the 3 tallest dinosaurs, well, we would just iterate over the result of this subquery and then check that we are only looking at those dinosaurs for which the rank is at most 3. So we are looking at the top and 2nd tier and the 3rd tier dinosaurs, and these would qualify, and we would then just output their data here. And that's about it. This is what we need to do. You just have to be aware what it means that you're using rank here. Dinosaurs that rank equally according to their height will receive the same rank. There might very well be 2 dinosaurs or 3 or more dinosaurs that have been assigned rank 2, for example. Okay, so these would then be admitted and they would be seen in the result here down below. You see the filtering is looking for any ranks that are less than 3. There could very well be more than 3 dinosaurs being output by this particular query, but all of their heights would rank in the top 3. Okay, if you replace this dash box with a row number, then indeed you would just strictly number the dinosaurs according to their height. Okay, regardless of dinosaurs of same height, each of these would receive a unique number inside their partition. So this query will indeed only output 3 dinosaurs maximum in each partition. Maybe this is what we want, then this is what we should choose, the row number function in the dash box here. Now it's a consequence of this choice that dinosaurs that rank equally according to height, the row number function will pick one arbitrary, one random dinosaur among these equally tall dinosaurs, and we will see that in the result. This is a consequence of our choice of using row number. Okay, one more thing here. You see that I'm using this subquery, all right. Subqueries are an okay construct, no problem about that, but one might wonder whether it's really necessary here. Well, we are on the outlook for this ranking value. It's just an integer value that is being computed, and you might expect to be able to replace this n here, which is just this integer rank, by this expression. by this expression which computes the n. All right, so let's circle it correctly. So that would be that expression that computes the n. But this is not possible. It's syntactically not valid to use window functions in general, not regarding row number or ranking. This is not specially a window function in general, may only occur in the select clause, of a SQL select from where block. Okay, so window function invocation only in the select clause of a SQL query. We cannot place such an invocation here and down in the where clause. That's no real issue. We can always formulate a subquery in which the window function invocation is located in the select clause and then use the computed values in predicates and wherever we would like. Okay, so that's the reason why we are working with a subquery here. Okay, one more example regarding the ranking and the row numbering. Okay, and it's one of my pet peeves when I'm reading academic papers. This motivated this particular example. It's actually an example about identifying consecutive ranges in a series of numbers and to bring some order into a series of numbers, let's say. And it has been motivated by papers that you find out there that look like this, blah, 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 as Knuth has shown John Knuth has written a lot of papers. There's a lot of good stuff to cite there, but often in papers you find a jumbled mess like this. Okay, as he's written in 5 and 2 and 14 and so on, blah, 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 lots of cool papers. I've just listed them here in any order. I arbitrarily and randomly encountered these papers. Looking up these papers in a bibliographic reference leads to some frantic page flipping back and forth, and it's just plain chaos. So I think it's a disservice to the readers of your papers, and you will never find, I hope, you will never find such stuff in papers that we are producing here at the database researching group in Tübingen. What we would rather love to write is this. This is shorter and more organized. So you see that there is references to a paper number 1 and a paper number 2 and a paper number 3. And I think the better way to reference these 3 papers would be just this consecutive range of papers in references 1, 2, 3 and in references 5 to 7. Apparently 4 is missing here. Otherwise, we could just reference 1, 2, 7. Okay. And then there's a single reference here, the 10, with no consecutive references. But the 13 and 14, they form a mini consecutive range of just 2 papers. We could use a dash here. We could use a plus sign. We could use the ampersand sign here. That's just design. So this is much more reader-friendly and much more nice to look at. Okay, so let's write a SQL query that converts the jumbled mess above into this very well-organized, consecutive range organized list of references below. So the output and the input and the output of this particular problem is of course tabular. We are talking SQL here. So this could be a table of references, and as you can see, it's completely jumbled and disorganized. 5 to something blah blah ends with 13. This corresponds to the jumbled mess above here. What I would like to output then, an output from which I could easily generate this nice string here, is this. An ordered list of reference that starts with 1 and then ends with the maximum number of reference. It's 42 in this particular case, and an indicator that there's indeed ranges going on. So the 1 and 2 and even the 3 that's not listed here would all belong to the same range R0, let's call it. This is some arbitrary identifier. It's just a criterion that assigns 1, 2 and the not shown 3 here to the same range, and I could use that information to produce output that looks like this. So convert this into this ordered and then range organized version. How to do that? There's many ways to do that. One way involves the row numbering function. Okay, so let's see what a query plan could look like. That would be the jumbled mess input. All right. We would then order all of these references just by in ascending order. So you see that indicated by the arrow here. It's going from 1 to 42 here. And now the cool thing is happening. We will then just use that information, that's integer information, and will subtract from that the row number. After we have assigned an ordering here, it makes sense to speak of a well-defined, well-designed row number of these entries. And you see I've just listed the row number, the numbering from 1 to 10 for these 10 references right next to the table here. If we use the reference number and subtract from that the row number, what you will get is this. And this already neatly groups the references into the unique ranges that we were looking for. Okay, so the 1, 2, 3 here, the consecutive references 1, 2, 3, they are all part of the same reference or range 0 here. Okay, 5, 6, 7 are part of the same reference of same range. I'm sorry about that. Same range 1 here. Okay. There's other ranges that only contain a single entry, range 3, okay, but there's more ranges here, like the range containing 13 and 14, which has been assigned the row identifier, the range identifier 5. Okay, so as I told you, these range identifiers are completely immaterial. We could just use any indicator here that allows us to group the individual references into these range groups. Okay. So why the subtract trick is working is I think should be obvious. So these three consecutive references, they do not deviate. I'm sorry. These three, they do not deviate from the numbering that the row number would assign. The 4 is missing, so the 5, 6, 6 and 7, they deviate by 1 from the row numbering that we have assigned here on the right. So all of these deviate by the same number. The 4 is missing here, and that affects the 5, 6, and 7. So we deviate from the consecutive row numbering by 1 in that group. All right. Okay, here the 8 and 9 are missing, so we were already off by 1, now 8 and 9 are missing, now we are off by 3, and this is indicated by the result of the subtraction here, and that would be the range identifier we are assigning here for the reference 10. Okay, right, and once we are here, we could easily post-process this to form a nicely looking reference string. I think this is also done in the example that I brought with me here. All right, so let's see how we can do that. Let's first create the jumbled mess of citations. I need a table for that, and I will just insert the citations here, as you can see, in a completely disorganized fashion. All right, so if we look at this, well, we get any order anyway, but this is chaos. Okay, no reader should be required to read this. Okay, so we will now perform our query plan, and it's just a two-step plan, very simple. Okay, we will start by defining the range identifiers. That's just a subtraction by row number. Okay, that's very easily done. So we will look at all the citations. We will look at them, of course, in the reference order, in the integer order, okay, of the reference numbers. And in that particular order, we will number them. Okay, this will be consecutive numbers that are going from 1 to 10. That number will be subtracted from the reference number itself. Okay, so that would be already the second step in our query plan. Okay, it's actually the major piece of work already done. And as you can see, we will output this intermediate result, the CTE ranges, when I execute this query. Let's do that. Okay, and we see just the result that we've seen on the slide. All right, so 1, 2, 3 have been assigned to range group 0. 13, 14 have been assigned to range group 5. Works. Okay, so now what I'm interested in is inside such a range, what would be the first and the last page? I would need that information to produce this nice output. The range goes from 1, 2, 3, from the first to the last entry inside the range group. So let's just group these rows by their range identifier and then simply access the maximum and the minimum reference value in that group. That's just simple grouping and minimum maximum computation aggregation. No window functions involved at all. And this is what you see here in the second step, the second CTE. Go over these ranges, exactly this table, group them by range. Okay, so let's put all of these into one group. Access the minimum and the maximum value here, which would be the 5 and 7. And that would be the borders of my particular range in range group 1. That this is range group 1, I would also output here. But that's not really the core. All right, so let's disable that and look at the result of the output CTE here. Okay, so this is what we get. There's indeed 5 ranges that we could identify. They are all now being grouped and occur only once here. And this first range goes from entry 1 to 3, and this from 5 to 7, and so on. Okay, so there are some entries that are indeed consisting only of a single entry, but so be it. Okay, so from here to some well-organized string output, it's really only a minor step. We could look at the differences of the first and last entries here, and we could decide based on these references whether we want to produce output that looks like this, 1 to 3 or 5 to 7, because the differences between the first and last page are greater than 1. We could just output the 10 if the difference between first and last are simply 0. That would relate to the 10 and the 42. And we could use a special notation if the first and last references are just spaced out by 1. So we could use something like this or like this. And this is all we need to do. And actually, I'm sorry about that. I brought this logic with me. Super simple to implement. Simple case distinction. Okay. So what we do here, we go over this output, over all these entries, all right? And what we will build is one large string that we can just cut and paste and put into our papers. The entries of this string will be separated by commata. Oh, okay. And of course, we will have them in order by this range identifier, so that the first entries indeed come first in the string that we are aggregating. So this is an ordered aggregate. All right, and the individual entries of that aggregate, well, they look at the difference between the first and last pages. If that is 0, then the first and last page are identical. So we just output the first page or the last page, they're identical anyway. If the difference is 1, we output using ampersand. If the difference is larger, we will output using a minus to indicate a span of references here. And that's all there is to it. And this is the output that we could generate. Take this, cut and paste it into your papers, and do a service to your readers. Okay, so that's the row numbering and the ranking functions in the window function family. There's only one tiny group of functions left. We will look at these in the last video, and then let's call it a day for window functions in SQL. I hope you will be around for that last video. See you then.